In this video, we continue our investigation of these highly Hamiltonian graphs. We've already talked about Hamiltonian connected graphs, and remember we had an ORA type result for this. That was if sigma 2 of g was at least n plus 1, we could guarantee that it was Hamiltonian connected, or if the minimum degree was at least n plus 1 over 2. Maybe I'll write that down. Sigma 2 of g at least n plus 1. This implied g was Hamiltonian connected. And if the minimum degree, right, it would follow then that if the minimum degree was at least n plus 1 over 2, this would imply g is Hamiltonian connected as well. So again, we're skipping Hamiltonian extension numbers, but we'll talk about pan-connected and pancyclic graphs, and we'd like to see is there an ORA type result, Dirac type result for this. So first off, what's a pan-connected graph? A connected graph of order n is said to be pan-connected if for each pair uv of distinct vertices of G, there exists a uv path of length L for each L between the distance between u and v and n minus 1. So the way to think about this is that given a pair of vertices in a pan-connected graph, we can find a path of any possible length between them, between the distance between the two vertices and n minus 1 is the idea. So, all right, let me illustrate this with an example. So here I have this graph. This is K6 minus 3 disjoint edges. So maybe I'll call it G1. And this graph is pan-connected. So we only have vertices of distance 1 and vertices of distance 2 in here. So let's say I pick this vertex and this vertex. The distance between them is 1. And so if I claim this is pan-connected, we should be able to find a path between these two vertices of length 1, length 2, length 3, length 4, length 5, and that's it. That's the highest length you could possibly get in a graph of order 6. And certainly we can do that. So path of length 1, that's just the edge between them. Path of length 2, there you go, there's that one. Path of length 3, 1, 2, 3, there's one of length 3. How about one of length 4? 1, 2, 3, 4. And path of length 5, well, that would be a Hamiltonian path. And there's a Hamiltonian path between them. So a path of length n minus 1 between any two vertices, that's the same thing as a Hamiltonian path. So that checks out for those two vertices. Now, what about two vertices that are not adjacent to each other? So take this vertex and this vertex. Now, obviously, they're not adjacent to each other, and so I can't find a path of length 1 between them. But that doesn't preclude this graph from being pan-connected. The definition of pan-connected says there's a path of length L between the distance between them and n minus 1. So the distance between these two vertices is 2, 1, 2. And so what this is saying is, okay, I can find a path of length 2 between them. There's that one. I can find a path of length 3 between them. There's that. I can find a path of length 4 between them. 1, 2, 3, 4. There we go. 1, 2, 3, 4. Path of length 4 between them. Path of length 5 between them. Again, that would be the Hamiltonian path. And so you can check for any pair of vertices this condition is satisfied, being able to find a path of any possible length from the distance to n minus 1. So this is a pan-connected graph. Now certainly, if a graph is pan-connected, then it's Hamiltonian connected, because if it's connected, there's a path of some length, or the distance between the two vertices is somewhere between 1 and n minus 1, and hence for any pair of vertices there would be a path of length n minus 1, or a Hamiltonian path between the two vertices. So this is a stronger property than Hamiltonian connected, right? That means pan-connected. If the graph is pan-connected, it implies that it's Hamiltonian connected. So it's even stronger than Hamiltonian connectedness. Let's take a look at this example, which we saw in the previous video. This one was Hamiltonian connected. And just to illustrate that it doesn't, go the other way, this is Hamiltonian connected, but it's not pan-connected. So why is it not pan-connected? Well, pick, how about this vertex and this vertex? The distance between them is 1. And so I should be able to find a path, if it were pan-connected, be able to find a path of length 1, length 2, length 3, length 4, so on and so forth, up to 5. So the issue here is I can't find a path of length 2 between these two vertices. So take these two vertices, there is no path of length 2, but the distance between them, let's call them U and V, but the distance between them is 1. So if it were pan-connected, we'd be able to find that. And so this is not pan-connected. Pan, of course, meaning all. And so this is connected for all the possible lengths. All right, so can we guarantee a graph is pan-connected? Sufficient condition for being pan-connected. That's theorem 6.20. G is a graph of order n at least 4, such that the minimum degree of the graph is at least n plus 2 over 2, then G is pan-connected. All right, the proof of this is in the text. I am not going to prove it because I'm trying to keep these videos, and it's okay if we don't see the full proof of it. Again, you should read through it on your own and ask me questions if you're not understanding some part of it and want to talk about it. So this is a nice result to guarantee that the graph is pan-connected. In particular, this first graph I showed you, the order was 6. So n plus 2 over 2 there is 4. And you can check this is a 4 regular graph. And so it meets that condition. It's guaranteed to be pan-connected. So yeah, what I'd rather spend our time on instead of proving this theorem is seeing, one, that this theorem cannot be improved. And that this theorem cannot be improved, and 2, why there's no Dirac Aura type result. So right, this would be a Dirac type result. It has to do with the minimum degree, sufficient conditions involving minimum degree. It's like a Dirac type result, but where is the Aura type result? So I want to answer those two questions. So this result in general cannot be improved. So what I mean by that is, can we make this any smaller? Could I make this, say, n plus 1 over 2 and still guarantee that G is pan-connected? So the answer is no. There exists graphs with minimum degree n plus 1 over 2, but not pan-connected. So this is an infinite class of graphs, and so that's what you would like for a sharpness type result like this. But I'll just show you for the smallest value of n that this will work for. So we're going to let n be odd, 2k plus 1, and we're going to let this be at least 7. And we're going to start with the graph k plus 1. Kind of awkward to say. So complete bipartite graph with partite sets. Partite sets, we're going to call them V and W, or sorry, V1 and V2. Partite sets, V1 and V2, where V1 will be the one of order k, and V2 will be the partite set of order k plus 1. So we'll start there, and I'm going to do this for, so example of this, I'm going to do k equal to 3 is the smallest value this works for, but you can generalize. 2, 3, 4. So there's my sorry, 1 second. Yeah. So there's my one partite set, and then I'm going to have my other partite set down here, which will be order 4. 1, 2, 3, 4. So I'm going to leave this partite set alone. Let me draw the rest of the complete bipartite graph. start here and then add some things to it. And again, read through the text to see a complete description. So the idea is I'm going to leave V1 alone. I'm going to leave this partite set alone. And then in V2, what I'm going to do is I'm going to connect a bunch of these vertices over here, let's say on the left-hand side, with a path leaving two vertices that aren't on the path. So in this case, that would just be a K2. And then I'll join the last two vertices also with an edge. So in this case, it looks like K2, K2, which is why the book does the next case up, does K equal 4, because then you can see this would be a path of length 3, or of length 2 here, and then a K2. I get why they do it. I'm just going to do the smallest case here. And so we can check here the minimum degree. So every vertex down in this partite set is going to be adjacent to K, and then at least one extra one. So yeah, the degree of every vertex in V2, let me say it like this. If U is in V2, then the degree of U is at least, so in this case, it'll be exactly, but when we have a path, we're going to have some internal vertices of the path, will be at least adjacent to these K, and then one more for the path or the K2. So that's K plus 1. And then up here, well, each vertex, I haven't messed with this at all, so it's adjacent to exactly the K plus 1 vertices down there. So if U is in V1, then degree of U is actually equal to K plus 1. And so this was a graph of order 2K plus 1. So let's see, 2K plus 1, that's my N. And remember what I'm trying to show here. I want my minimum degree to be N plus 1 over 2. So that's my N plus 1 over 2. What's my magic number here? This is 2K plus 2 over 2. That is K plus 1. So the minimum degree of G is equal to K plus 1. So good, it satisfies that. And then the claim is that this is not pan-connected. So to see that, focus in on this vertex here and this vertex here. They're adjacent, so length 1 between them. There's a length 2 path between them. However, there's no path of length 3 between them, right? I would have to go 1, 2, 3. Sorry, no, those two are not the right two. There is a path of length 3 between those two, my bad. Are you with me? You're checking? Good, hopefully. How about these two? So they are distance 1. Okay, great. There's path length 1 between them. There's a path of length 2 between them. Is there a path of length 3 between them? Well, this guy's adjacent to the only thing up here in that partite set. So I would have to go up to one of these. And unfortunately, I couldn't go back down. That would only be a path of length 2. So I'd have to come over to one of these vertices, and they're not adjacent to this one. And so there's no path of length 3 between these two vertices. So the distance, let me call this x and y, distance between x and y is 1, but no path of length 3 between them. And so this is not pan-connected. So that's showing that this theorem above is sharp. We cannot improve that condition at all. Can't improve that condition at all in general and guarantee that the graph is pan-connected. You might be able to guarantee it in special cases. For example, maybe if you have even ordered, these are all of odd order. Maybe if you restrict yourself to even order graphs, maybe you can change it. But this is, in general, you can't change it and still get the same general result. So, okay, so that was question 1 answered that I posed, which was, is this best possible? And yes, it is best possible. It's a sharp result. The other question was, where is the Dirac type result? This theorem was not proved. Most of the time we prove these minimum degree ones based on the Dirac type result with the minimum non-adjacent degree sum. We weren't able to do that this time, and there's a very good reason for that. So where is the Ora type result? There is no value c, right? We would want a result something like sigma 2 of g is greater than or equal to. Remember, we had one like for n plus 1, guaranteed Hamiltonian connected. But there is no value c that you can pick such that if sigma 2 of g is greater than or equal to n plus c, that guarantees that the graph is pan-connected. So this shows you, yeah, there's no result of this exact type to guarantee that G is pan-connected. It doesn't follow the same pattern as the other ones. And so this kind of, yeah, it breaks the pattern. It's pretty interesting why pan-connected messes everything up. If you want, ask me about my own research into k-uniformly connected graphs, or choose this for your project, and you can go into, there are some aura-type results that give similar results to pan-connected, but not quite pan-connected. It's more specific than pan-connected, yeah, or a little bit weaker than pan-connected. But there are some results you can do. So why is this the case? So if we're claiming this, well, we should be able to prove it. We should be able to prove there's no result like this. So how do we prove something like that? Well, let's see, be an integer, at least 2. We already know, yeah, c plus 1 doesn't work because we know there's a Hamiltonian connected graph that's not pan-connected. We can assume c is at least 2. And I'm going to make a graph. I'm going to let the order of the graph is going to turn out to be 2c plus 4. And what it's going to look like is how I'm going to build this. I'm going to take a vertex u and a vertex w. I'm going to let these be adjacent to each other. And what I'm going to do is I'm going to make 2 sets down here, u and w. So this guy's going to be u, this one's going to be w. Maybe I'll actually label it under the picture. This is u, this is w. So this in general contains, this is going to be c plus 1 vertices in each one of these. So c plus 1 vertices in here, c plus 1 vertices in here. So size of u, or order of u, order of w, is are each c plus 1. And then I'm going to let u be adjacent to every vertex in u, and w adjacent to every vertex in w. And that's it. This is my graph. Well, not the full story. I'm going to let all of these vertices be adjacent to each other. So this is going to form a k 2c plus 2. I'm going to let all the edges between these vertices be there. I'm not going to picture all the edges because it would get really, really messy. So this is a big complete graph, and then I just have these 2 vertices here. So, okay, so we want to check that the minimum non-adjacent degree sum is satisfied. Well, let's see, u's adjacent to everything here, so I have to check pairs of vertices like u and things in w. I have to check w and vertices in u. I don't have to check any pairs down here because they're all adjacent. And remember, we look at non-adjacent degree sum. And then u and w are adjacent, so I don't have to check those. So I really have to check degree of u plus degree of x, where x is in w. And honestly, by symmetry, we don't have to check the other case. We'll just check that. So degree of u, it's adjacent to these c plus 1 vertices. And then w, so that's c plus 2, plus the degree of the vertex down here. So it's adjacent to, this is in a complete graph, 2c plus 2. So it's adjacent to 2c plus 1 other vertices in its little complete graph down here. And then it's also adjacent to w. So it's a 2c plus 2. And so that's a total of 3c plus 4. Wait a second. Let me double check that. Right, so that's what we wanted. Because 3c plus 4, my n is 2c plus 4. And so this is really n plus c. right? So I have that, so we have sigma 2 of G is at least n plus C. Great, it satisfies the degree sum condition for any C that you picked. And I want to show you that it's not pan-connected. So let's see, which two do I want to pick here? Well, how about this one? How about this? How about U and W? So the distance between U and W is 1, so it should see a path of every possible length. However, there's no path of length 2 between them, because U is only adjacent to these vertices, so I'd have to go down here to some vertex here, and then there's no way back up to W immediately. I'd have to travel over here and then up. And so there's no path of length 2 between U and W. So no UW path of length 2. So it's not pan-connected. So sigma 2 of G is greater than or equal to n plus C, but not pan-connected. So that shows you that there's no type of result of that form, sigma 2 of G being greater than or equal to n plus C, that's going to guarantee that the graph is pan-connected, because I can always give you this as a counterexample. So that's pretty neat. And it's a little bit disappointing that this trend doesn't continue of having an OR type result and a Dirac type result. Now, there's maybe a little smidgen of that being saved. While there's no OR type result for this, and really the natural thing, the way I presented this would have been n plus 2, there is an OR type result for a related definition. So we say a graph of order at least 3 is pancyclic if it contains a cycle of every possible length. So between 3 and n minus 1. And then there's a theorem which says that if you have a graph of order at least 3, such that sigma 2 of G is at least n, well, then with at most one exception, G is pancyclic. So G is pancyclic, or n is even, and G is this complete bipartite graph, balanced complete bipartite graph, Kn over 2, n over 2. So maybe that, I don't know, doesn't quite save it, but we have that. So yeah, if you want to see this, I don't know, maybe saved a little bit more, you can ask me about the uniform spectrum of a graph. I can tell you a little bit about my own research into this. Okay, that's it for this video. In the next video, we'll get into section 6.5, talk about powers of graphs and line graphs. I'm excited.